photonic interconnects between chips on a board, and in the very, very long term, we are looking at research where we will replace the interconnects within the chip, connecting sort of hundreds of cores on a chip using optical interconnects. Now that's really, really long in the future, and HP today we don't manufacture sort of CPUs, as you know, so there the approach is to partner with the chip vendors like Intel, AMD, and others to make sure that these kind of technologies will eventually make it so that DesignCon engineers can actually design those kind of systems. So that's what I'm going to talk about. I'm going to talk about the shorter term work on optical interconnects on the optical bus, the medium term, and the long term. So let's get started on our work on the, before I do that, let me look at sort of again, the photonics portfolio. So if you look at the sort of telco world, many of you may say, hey, what's the big deal? People have been using photonic interconnects today in the telco world, right? You connect up sort of the Americas to Europe through the optical cables that you do under the Atlantic Ocean. True, but those technologies use optoelectronic couplers which cost sort of thousands of dollars, sort of $5,000 for a part in sort of New York to connect up your electronics to the optics, and then that goes down the fiber, right? And in London you have another optoelectronic coupler that takes you up, and these two ends are $5,000 a piece. Now, so you can say conceptually, all you have to do is do the same interconnects for computers, right? Now you have a computer having 1 million CPUs in your data center. You add $5,000 parts to your 1 million CPUs, your cost of a data center is going to go sort of completely wacky. So the question is, can you come up with low-cost ways of bringing optical interconnect technology to the computer industry, something that has been there in the telco industry for the last 30 years? That is the key challenge. So today, in the computer industry, people have been using sort of active optical cables to connect up sort of connectors in the backs of servers. But what we are doing at HP Labs, we have just demonstrated this concept of optical bus, which is sort of today's technology that you can use this to take this optical cable to the next step. In the future, we are looking at integrating sort of 3-5 semiconductors, the photonic layer in a hybrid way, photonic layer on top of silicon in a hybrid manner. But in the long term, we're looking at sort of silicon photonics, where we will be able to connect 256 cores on a chip using CMOS technology, and the connections will be through optical interconnects. And the picture on the right-hand side shows a Corona architecture that HP Labs researchers came up with to do kind of that vision. But that's 7-10 years into the future. So now let's look at what we have done in the short term. The first, most practical work is the work on electrical backplanes. So as I mentioned, if you look at sort of server designs, bladed servers and so on, networking, large switches and so on, you have these sort of CPU boards that need to communicate to other CPU boards that need to communicate to I/O boards, to memory boards and so on. And all of those are happening from the CPU board. You have to go across to the backplane, and then from the backplane you go back into the memory board. Each time you go from one board to the other, you're going through power losses, right? So you have this standard sort of capacitive stuff that is going through. You have delays, large delays, lots of power, and so on and so forth. That's kind of today's technology. And we want to replace that backplane through optical interconnects. So what we have done at HP Labs, in fact, some of the researchers from HP Labs are actually in the audience today, is to come up with a concept of an optical bus. So all of you at DesignCon, you know the concept of electrical bus, right? It's kind of basically a piece of wire on which a master puts some signal on it, and everybody listens to that wire, and the slaves pick up signals from that wire, right? That's the concept of a bus. Now to do it in optics, right, there is no concept of electrical signal, there is no capacitance on which you put charge on. So you are now dealing with light, right? So imagine a master pushing light on an optical bus. So you took the light and you're just putting some ones and zeros in optics on light on a line, right? So for the slaves to listen to the bus, right, you have to have some kind of emitters to reflect that light. So when you see those things like BS1 and so on, those are the emitters. So you essentially have, to implement an optical bus, you have two unidirectional buses, one from the master to the slave, the other from the slave to the master, and at every point, when you want to go from master to module A, you put in an emitter, conceptually, right? But if you put in a mirror at 45 degrees and it's a full mirror, then essentially all the light gets reflected up and nothing goes to the follow-on part. So what you have to do is, suppose you have 4 taps, the first mirror needs to be 25% reflective, right? The light goes in, 25% of light goes out, and 75% goes through. It's like a translucent thing. The next mirror has to take another 25% and let 50% go through. The next mirror has to take another 25%, let 25% go through, and the last mirror is fully reflective. So you have to come up with a concept of changing reflectance based on the position of the taps. And you do the same thing on the way back. So that's kind of the high-level concept. Now you do this using optics. You do it with sort of optical sort of technology which I'm going to talk about. But the key concept is how using some MEMS technologies, using silicon nitride layers and so on. So there's some cool stuff that has gone on at lab to do these different reflections, phase reflectance depending on the number of taps. So now we have actually put this thing together, and to show that this is real, this is what a 30 centimeter, a 12-inch optical bus looks like. You take something like a plastic injection molded stuff, right? This is just a piece of plastic, right? You can buy it for $1. Now, inside that, you think of a waveguide, which is like think of it like a straw. And within that, you put metal, copper, aluminum, whatever, which is this shiny metallic stuff. So imagine a straw on which the inside the thing is completely metal and it can reflect light. So you put highly parallel collimated light through this hollow metal waveguide, and you set it from this side, it will go on the other side. But that is just a bus, and it cannot read or write off the bus. So you have to put in these little windows to listen to that light, right? So this particular thing is showing that if I now put on this hollow metal waveguide, you put these taps, and that's what is shown on this thing. This shows this hollow metal waveguide. These are the optical fibers coming in through optoelectronic. It's just that light is going through. There are 12 channels in this hollow metal waveguide, and there's these 6 taps. To make it low cost, there are these guide pins, so if you want to connect up something, it just clamps on, just like Lego building blocks. So the concept is we have built this at HP Labs using our demonstrator program to make it really, really low cost. The cost of this is $10, not the $5,000 that people use in the telco industry. So now, does it work? Yes, it does. So we used all the sort of design instruments that DesignCon engineers use all the time, the eye diagrams, right? You look at these multiple taps. There are 12 channels in this hollow metal waveguide running at 10 gigabits per second, 12 of them running at 120 gigabits per second. And you look at those eye diagrams, they look pretty good to me. They look like eyes, right? And if they all look like perfect eyes, that means good things are happening. Perfect signal integrity. The power loss is 0.06 dB per centimeter. So it's fantastic, really high quality, good optical waveguide. So we proved that, right? Then what you do is you take this optical bus and you build it in a system. So this year what we did is we took one of our HP's largest, most powerful switch, the 9200 switch from Procure, and we replaced the backplane of this switch with this optical